Hi there, guys. Well, welcome back. We're about to work on the examples which lead towards 3M. Well done on your efforts for the last exercise. The fundamental theorem of algebra is a lot to take in. There's a lot of little ideas there, and there's some difficult questions which we went through. Hopefully, this next bit is going to be a bit easier. So we have the sum and product of polynomial roots. So if we have our roots, for example, if our roots are x1 and x2 for a quadratic, if they give us zeros, then there are conditions for the sum and the product of those roots, so x1 times x2 and x1 plus x2. And not only conditions, there are formulas, and those formulas extend pretty nicely for not only x squared, for quadratics, for cubics, for quartics, and so on, for polynomials of order n or of degree n. There are nice little formulas, and here are the formulas. This is the cubic formulas, in fact, so I think I've copied it here. So here's me. So given this polynomial here, saying if given this polynomial here with real or complex coefficients, so it doesn't matter if we have complex coefficients either, and these zeros, in other words, that it can be factorized between x minus x1, x minus x2, all the way up to x minus xn, and then you can put obviously an a in front as well. In fact, you'll get a n in front because that's the only way of getting x to the power of n. So if we can, if this thing here basically can be written like this, that's fundamental theorem of algebra, and given that, we end up with the sum of all of our x values which give us the zeros, or the sum of the roots here is going to give us our negative second term divided by first term coefficient. Okay, and the product of all of these roots is going to give sort of an alternating -1 or 1, depending on how many the degree of the polynomial which we have, and then it's going to be the last term divided by the first term coefficient. Okay, now we should try and prove these. In fact, it's not too difficult to prove, and in the book they ask you to go through various investigations here, and we're going to just start off by showing that this is true with a quadratic. So let's just come up with ax squared plus bx plus c is equal to, and let's come up with that a again. We've got x minus x1 and x minus x2. Okay, now if we look at both sides, if we compare both sides by multiplying this out, we should end up with these formulas here, or at least these formulas for when n is equal to 2. So when we multiply out the brackets on the right hand side, we see that we're getting x squared, we see that we're getting minus x1 x minus x2 x, and we're also getting plus x1 x2. That's obviously all being multiplied by a. Now if we multiply this out and do a bit of factorization here as well, we can say that's ax squared, and then we've got minus a x1 and x2 lots of x. Hopefully you can see that that gives us out each of our middle terms there. So we've got a lots of this thing here is the same as a times x1 times by x. And so that's the two middle terms factorized, and then we're bringing in the a, and then we've got the x1 and x2 on the end as well. Okay, so if we compare both sides here, okay, so if we compare, for example, let's compare the last term to start off with. So if we compare x to the power of 0, we can see that we're getting c is equal to x1, x2. Not true, because I'm missing something. I wonder if you can see my mistake here. I'm missing my a here. I forgot to multiply by my 8 there. Okay, so again, comparing both sides, that didn't seem right. So we're getting a x1, x2 is equal to our c. So we see that the product of our roots here is equal to c divided by a. Now, product of the roots, we're being told from this formula here, is -1. In our case, we've got squared as our highest power, so we're going to put in n is equal to 2, and we've got a0, which is equal to c, and then divided by the first term. So it's the last term divided by the coefficient of the first term. So divided by a, and that's of course just equal to c over a, because this is going to be +1. So there we go, we're verifying that this is true, that this rule is true for quadratics. Now, let's look at the other term here. So let's look at this one. And we can see that we're getting the sum of our roots in our middle term here. So in our middle term, if we compare our x to the power of 1, we can see that b is equal to -a x plus 1 x plus x2. Okay, now if we do a division there, we can clearly see that we're getting x1 plus x2 equal to -a over b. In other words, that's minus, mistakes here. Okay, that's minus b, that's the second term divided by the first term, coefficients of those terms, that is. Okay, so we've got minus that. So this is the same as this thing here. We've just verified that this is true of a quadratic. Okay, well, I'm going to continue this with a cubic, and then I'm going to show you the general case. And so the general case is actually pretty straightforward to work out, but we're going to kind of do it through the cubic to start off with. So same thing again, start off with the cubic. So any cubic is going to be ax cubed plus bx squared plus cx plus d. And that's going to be equal to a lots of x minus x1, x minus x2, and x minus x3. So our three roots there are x1, x2, and x3. So we're just writing the whole thing in a different form. Okay, now I could spend some time multiplying this out, and that would take quite a long time, and that would come up with quite a lot of algebra, and I'm quite likely to make a mistake at some point during that. Okay, but in fact, it's pretty easy to see how we can get the formula for the product of the roots, and we can get that by doing the last terms times together. So in other words, if we consider the case of x to the power of 0, okay, so if we compare the coefficients of x to the power of 0 on both sides, we get d is equal to a, and then we've got minus x1, minus x2, and minus x3. Now, again, you can see that when we have three roots, we're going to end up with a negative answer. When we have four roots, we'll end up with a positive answer there, because of course we've really got there this -1 to the power of n each time. Okay, and that's where the -1 to the power of n is coming from in this formula here. So if we want, we could factorize this out and say, well, that's equal to a and -1 to the power of n, and then x1, x2, x3. Okay, now clearly if we rearrange this, we're getting the product of our roots here, x1, x2, x3, is equal to d over a -1 to the power of n. And that's exactly what we're getting here as well. We're getting the last term divided by the coefficient of the first term, and there's our power as well. So that one's quite easy to see. Okay, now it's less easy to see where the sum of all of these things are coming from, but not too tricky. So what we're going to do is actually look at comparing what's happening with x squared on both sides here. Now, in fact, if you look at the formula here, we see that this is actually the coefficient of the second term. So that's why we're considering the second term here. Well, so the coefficient on the left-hand side is equal to b. Now we've got to think about how we can get out x squared from the right-hand side here. Okay, well, let's think, how do we get out x squared? Well, we can do x times x times this minus x3. That's one way. We can do x1 times x, that's a second way. Or we can get out x squared by doing x times minus x2 times by x here, that's our third way. So there's three ways of getting this. So in other words, we're going to have minus x1 lots of x squared. We're going to get minus x2 lots of x squared and minus x3 lots of x squared. That's coming from multiplying out these brackets because there's only three ways of getting out an x squared term there as we bounce between the brackets. Now, of course, we have an a on the front here as well. And at this point, you can see that you can factorize this out pretty nicely. So we can see that you're always going to be factorizing out the minus. Let's factor out the minus. Let's do the b, and let's factorize out that minus, leaving all this positive. Let's divide by the minus a. So we're getting minus b over a. Then we're getting x1 plus x2 plus x3. Okay, and obviously that's giving us the same thing as doing the coefficient of the second term divided by the coefficient of the first term with a minus on the front. Okay, so now we're going to take that to a general case. And if you're not so interested, I'm also going to talk about this and this in a little bit too. To talk about that at the end of the general case. We've done this with the cubic one, so now let's extend that to the general case. And in the general situation, we've got an x to the n plus a n to the minus 1, not the minus 1, a n minus 1, that's as a subscript there, and we've got x to the n minus 1 plus, and continues on until you get your last two terms. You get a1x and a0x there as well. It's going to be an a. Feel that bit better. Okay, a. Okay, so that's going to be equal to, and again, we're going to say that's equal to our factorized form with all of these roots. So we've got x minus x1, x minus x2, all the way up until x minus xn. And remember, we can put an a in front here, but this time around, we're not just putting a, we're putting an. Of course, there's only one way of getting x to the power of n. When you times all of these things, the front together, and then so we're going to need this coefficient of a to the n as well. Okay, so that's our general format that we can start off with. Now let's deal with the easier thing first. So let's deal with x to the power of 0. And with x to the power of 0, we can see that we're getting a mistake in there. That should be x to the power of 0 there. So that's just our last term. So with x to the power of 0, we see that we're getting our coefficient is a0. That's going to be equal to an. And then that's times by each of these things here. So we're getting minus x1 times by minus x2 all the way up to times by minus xn. Now we can see that we can factorize out again our minus 1 to the power of n. We've got a to the n there, and now we've got the multiplication of all of these terms. So we've got x1, x2, all the way up to xn. That's equal to a0. Now, of course, a little rearrangement of that gives you this formula here. So again, let's just remind you, it's last term divided by coefficient of first term with minus 1 to the power of n in front of it. And that's exactly what we're getting here. Okay, right, well, that's that one. And now if we take the second term again, just like we did with our cubic, so we're taking here x to the power of n minus 1 and comparing coefficients. So coefficient is going to be a n minus 1 is equal to, and again, remember that there are n ways of bouncing between those brackets to give you a n to the power of minus 1. N to the power of minus 1. Now, I'll leave that in there just for a moment, but actually we're just comparing coefficients, so that's going to disappear. But how are we going to get that? Well, we could do this like bouncing between many ways and then hitting this one. Okay, so we're going to get, let's put it over here, okay? So we're going to get minus xn, let's put that at the end actually, minus xn lots of this thing here, but we're also going to get minus x1 lots of this thing here, so we get minus x1, and we're going to get minus x2, and minus, and so on, all the way up until minus xn. And then, of course, we've still got this an at the front here as well. Now, we can factorize out the minus. This thing disappears because we're actually only interested in coefficients, because it's essentially disappeared from that side as well. So now we just need to do the divide by the minus and the divide by an, and we're getting our sum here. So let's write it round an minus 1 divided by an, divided by the minus as well, and we're left with this x1 plus x2 plus all the way up to xn. So there we go, we've shown that the formulas are true there. Okay, so now we're prepared. Now we're at a position where we can now have a go at the questions. But we should just remember another way of writing this down could be to write the summation of all of our xk's from k, not I, could have written I if I wanted to, it's just a dummy variable, from k is equal to 0 up until n. So the summation of all of these things is the same as saying this thing here. Not 0, 1. Okay. So that's the summation of our n roots. This is another way of saying this thing here. Now, we know that one already, but how do we say all of our roots times together? Well, instead of using this sigma, this capital sigma here, we're going to use this capital pi. And this means that we're not adding together all of our terms, but we're timesing together all of our terms. And again, we can say this is from k is equal to 1 up until n, and that's of xk. And that's saying this thing here. That's the same thing. Lots of mistakes today. So that's saying this thing here, the product of all of these things. Okay, so let's look at the questions. So there's another investigation there. And we've got example 31 is our first question. So take the first question. Now, these formulas do turn up in our formula booklet as well. So you can always use these. Remember what they were. We've got minus 1 to the power of n. And we've got the last divided by the first coefficient. Just writing it down in a way which you might remember. That's the product. So there's our product. And then, or we can find that as our I, if you like. And then sigma is always going to equal to minus the second divided by the first. Now, I have to say, because I don't use these formulas all that much, I generally need to refer back to the formulas in the formula booklet as well. And that's why I've written these down at the top. Okay, so example 31, it says the roots of the cubic equation here are x1, x2, and x3. Without solving the equation, find these things here. So the summation of the roots, again, is the second coefficient. So this one is just equal to the second coefficient, which is 5, divided by the first coefficient, which is 3, and then put a minus in front of it. So there we go, minus 5/3. That's it. That's done. For the next one, we've got x1, x2, x3. And again, we're doing the last term here, divided by the coefficient of the first term, okay, which is 3, and then times by minus 1 to the power of 3. And minus 1 to the power of 3 here is going to give us out, let's just put that on here, times by minus 1 to the power of 3. It's going to give us out minus 1, so the answer here is going to be 4/3. Okay, so I've just stopped the video. I've gone through the next part, and I did it in a different way to the book. So because I was a little bit plodding going through that, a little bit slow, I've just shown you what I've done for part C here. So the way in which I approach this is not necessarily the best way, and I think actually the book way is actually better. So for part C, okay, so we can see that's where we finished off for part B. So part C starts up here, starts here, goes over here, and it goes over here, okay? Now to start off with, I thought, well, I don't know what x1, x2 is, but I know x1, x2, x3 is equal to 4/3. We've got that from part B. So then I did a rearrangement of that, and I did x3 is equal to 4 over 3x1, x2. And I did that in the same way for, so there we go, that's the same thing there. And then, sorry, I've taken the 3 across and I've divided by the 4 as well. So there's my expression for 1 over x1, x2. So I created that from this thing here. Now I created another expression in a similar way because of the sort of symmetry that we're getting here for x2. So x2 was equal to, again, 4 over 3, x2, x3. And then again, by taking over the 3 and taking the 4 to the other side, we're getting an expression for 1 over x2, x3. That's this thing here. Now, likewise, you can do another expression for the middle one in a very similar way. And so we just end up saying, well, 1 over x1, x2 is equal to 3x3 over 4, okay, or 3/4 x3. And I've done exactly the same with the other two expressions. They're using these things here. Now, I factorized out the 3/4, and I'm left with x1 plus x2 plus x3 inside there. And then I've substituted in my x1 plus x2 plus x3. So I've done 3/4 times by minus 5 over 3. I've simplified it and I've got the answer of minus 5 over 4, which is fantastic, but it's not necessarily the quickest way of doing this. Now, the way the book does this is it just says, well, let's make an equivalent fraction here. So let's make a fraction with a common denominator. So just times the first one by x3 over x3 and so on, with the second one x2 over x2, and with the third one x1 over x1. And you can see that the book is then getting out, this question again. Sorry, you're not there. We're here, sorry. So the book is then saying, well, look, if you make an equivalent fraction, just a single fraction here, an algebraic fraction, we've got the sum of our roots on the top and the product of our roots on the bottom, and that's much quicker. But I have to say, I didn't see that. I was just playing around with the algebra. And perhaps I should have seen that. But again, in a situation, this is a non-standard question here. And in an exam situation, you've got to be prepared to think, okay, how do I play with what I know in order to make some substitutions and see if I can get the answer to what they want. So I found expressions for each of these things by using part B, and then I could see that the other part popped out. Okay, so there you go, two different approaches, and probably the book approach is nicer in that case. Okay, so next question, we've got example 32 before the exercise. So example 32, let's just take this one. Okay, so it says find the sum and product of the zeros of the following polynomials. And again, I'm just going to write down for my own understanding or my own satisfaction here. I'm just going to put down that the product is minus 1 to the power of n, and we've got our last divided by our first n, and we've got the summation is equal to minus the second over the first. Okay, so for part A, finding the sum and the product of the zeros in the following polynomial. Now they're calling them the zeros here, but they're also the roots, of course. So for the sum, first one's super simple. We're going to do the second one over the first one with a minus in front, which is going to give us minus 1. And the product for that one is going to give us, well, minus 1 to the power of 4 is just plus 1. And the last divided by the first is just going to give us minus 2. Super simple. Okay, so for part B, so that's A, we're going to do exactly the same thing again. So actually that one's pretty dull. I mean, you can do that yourself. I'm going to actually just do C here. Okay, so there's no problem with getting the practice, of course, but you know, just there's nothing much more really to that one than the practice from the first one. So for C, we can see again we're going to get the sum is equal to the second coefficient divided by, well, that's interesting actually, because the second coefficient is actually not 7. The second coefficient doesn't exist. Oh, there's a little trick to that question, because we've got x to the power of 2018 times by 0. They've kind of missed out the middle terms here. Okay, so our second term is 0. So the sum of our roots here is actually going to be equal to 0, which is kind of interesting. Okay, and for the product of our roots, again, the product of our roots is going to be minus 1 to the power of 2019, and then we're going to do 21 divided by minus 5. Now, this is obviously going to give us minus 1, so that's an odd number in the power on top of minus 1. It's just going to give us minus 1, so this is just going to give us 21 over 5. Okay, just check those answers with the book. So we're getting 21 over 5, and we're getting 0 there. And the answers to B, if you had to go at B as well, is equal to 5 over 2 and minus 4. Okay, another little thing there is it says, notice that for these formulas, you only need to use 3 coefficients. Again, I find that kind of interesting that the sum of all of these roots and the product of all of these roots, you know, that boils down to just 3 important coefficients from our original polynomial here. So yeah, there we go. And so your exercise here is 3M, so 3 questions on 3M. And next time round, we're talking about solving equations and inequalities. Looks like we're back to simply solving in real terms to start off with. They're not complex numbers. Okay, well, thanks for listening, and hope to see you for the next one.